Okay, guys, the next topic is topic 9, which discusses nuclear decay. I have to admit that this is a topic that is very close to my heart, as I studied nuclear physics for many years of my life. So before we mention anything, let's mention what nuclear physics is. So nuclear physics is the study of the properties of the nucleus of the atom. And when we say properties, we mean how these nuclei move, so motion, what kind of energies they have, how they decay, which is the topic of this video. So decays, how they react, etc. Okay, so nuclei can interact with each other and various things can be observed. So what is the nucleus? Like if we draw, so if this is a proton and this is a neutron, usually what is that cartoon like when they draw atoms? Something like that, I guess. So these are the electrons, okay? Don't know why the circle disappears, but yeah, you get the idea. So the atom consists of electrons, protons, and neutrons, and we will study the nucleus, which is in the center of the action. Okay? Now, some nuclei, and I have to warn you that this is going to be a long video because I made a lot of notes about this. If it gets too long, I'm going to split it into 2 videos. We'll see. So some nuclei are unstable. What does that mean? Meaning that they have excess energy which they release by emitting particles. And these unstable nuclei are called radioactive nuclei. What kind of particles do they emit? It can be anything, but the most popular types of decay are, I'm going to write it here, 3 types are the most popular. Alpha decay, and an alpha particle is the helium-4 nucleus. Okay, actually I have to specify that. Helium-4 nucleus. So if we go back to this picture here, the helium-4 nucleus is what's in the middle, okay? So it's the helium-4 atom with the electrons removed, okay? So that's the first type. The second type is beta particles, and we denote this as 0, -1. And by the way, I forgot to mention that 4 means 4 protons and neutrons. That's the mass number of an alpha particle. And 2 is the atomic number, which is the number of protons and electrons. Okay, in the case of the alpha particle, there are no electrons. So 2 is the number of protons. So the atomic number tells you which element you're dealing with, and the mass number tells you its mass. Okay. A beta particle has 0 mass because of beta part, and an atomic number of -1 because it's an electron. Okay. So beta particles are electrons. Why did they name them beta particles? Because back when these things were discovered in the late 19th century by Henri Becquerel, a French scientist, I think the idea was that this type of radiation was unknown, so they just gave it Greek letters, alpha, beta, gamma, etc. Okay, and the last one is gamma, which I just mentioned. So gamma particles have no mass and no charge, and these are photons, okay, with very low wavelength, okay, as we will see. I'm going to mention more about this later. So let's now talk a little bit about radioactivity. Radioactivity is actually a natural process, okay? So as we speak, we are bombarded by radiation that comes from the atmosphere and the soil, etc. So it's something natural, and we are built to withstand some amounts of radiation, okay? But an excess amount of radiation can be dangerous for humans. So radioactivity is a natural process, and it's harmless for environmental levels. And what do we mean by environmental levels? Anything that emits radiation with a rate of about 0.5 counts per second. Now, what does that mean? It means pretty much 1 count every 2 seconds, meaning that one alpha particle or one beta particle or a gamma particle is emitted every 2 seconds. Okay, so that's the environmental level of radiation. Okay, what causes this environmental radiation? So environmental radiation is due to, let's see, radon gas at about 50%. Radon gas is a noble gas. It's in the same family as helium-4, neon, I think it's neon-20, argon, xenon, etc. It's radioactive. It's very heavy. I should remember its mass number. I think it's in the 220s, something like that. And so because it's heavy, it concentrates in basements. So you have to make sure that your basement doesn't have radon gas. I think in the US it's mandatory to check that, and probably in other countries too. So radon gas is responsible for 50%, about 50% of environmental radiation. Let's write down this one. The buildings and rocks are responsible for about 14% of environmental radiation. And this is because they contain uranium and other kinds of heavy elements that are radioactive. Food and drinks are responsible for about 12% of environmental radiation. The first thing that comes to mind are bananas. Bananas have potassium, and potassium-40 is radioactive. It emits, I think, beta particles and maybe gamma. I don't remember the specifics. And then cosmic rays, maybe you heard of those before. This is radiation that comes from space, pretty much. So it's radiation emitted from other stars in other galaxies, and or inside our galaxy, or the sun itself. So that's responsible for 10% of environmental radiation. And another cool thing about cosmic rays is that pilots fly high up in the atmosphere, so there are higher amounts of radiation higher up in the atmosphere because it's thinner than compared to down here on Earth. So pilots can only fly that many hours, I think, every year. So it's one of the rules because they get exposed to more radiation. And the same goes for the crew of airplanes. Now, let's talk units. So 1 count per second is called 1 becquerel. Becquerel, in honor of the scientist who discovered radioactivity. And yes, that's kind of like trivia so far. Now let's take a deeper dive into nuclei. So deep dive. Let's talk about the mass deficit of nuclei, pretty much, and binding energies and stuff like that. So if we measure, we will take lithium-6 as an example. So if we measure the mass of lithium-6, and lithium has 3 protons, okay? So 6 means 3 protons and 3 neutrons, and 3 is the atomic number, meaning 3 protons. So if we measure the mass of lithium-6, we will find it to be less than the mass of 3 protons and 3 neutrons. So the mass of 6 lithium is less than 3 times the mass of 3 protons and the mass of 3 neutrons. Okay, and I will discuss about why is that, but let me give you some numbers first. So the mass of 6 lithium is 6.015 123 U, and 1 U is U is the atomic mass unit. We mentioned it when we studied gases earlier. Okay, now the mass of a proton is 1.007276 atomic mass units, and the mass of a neutron is 1.008665 atomic mass units. Notice how close these the mass of the proton is to the mass of the neutron. Okay, so they are about the same particle in terms of mass. Now, you don't have to memorize these masses. In problems, they will be given to you. And I owe you to the definition of what 1 U is. So one atomic mass unit was mentioned in the video about ideal gases is 1.66 times 10 to the negative 27 kilograms. And it was defined as 1/12 of the mass of carbon-12. Oops. And I think in chemistry they call it the Dalton. I should remember this, but oh well. So, okay, let's move on. Now, let's add. Remember when I said that lithium is lighter than the mass of 3 protons plus the mass of 3 neutrons? So let's go check that. Let's define delta M to be 3 times the mass of the proton plus 3 times the mass of the neutron minus the mass of 6 lithium. If we do this calculation, we will find that this delta M is 0.0327 atomic mass units. And if we convert to kilograms, it's 5.43 times 10 to the negative 29 kilograms, okay? And this delta M, so you see, I didn't lie to you. There is a mass difference, okay? And this is called delta M, is defined as Z times the mass of protons plus A minus Z times the mass of neutrons minus mass of X, okay, where X, A, Z is the nucleus under question, okay, and this delta M, so delta M is defined as, let me put it in a red box, okay, and delta M is called, actually let me put a full stop here. So delta M is the mass deficit, okay, deficit, which is positive, sorry, for all nuclei. And if I don't forget, I'm gonna provide a table, a link in the description where you can go find the masses of multiple nuclei and you can test this, okay? So mass deficit is positive for all nuclei. Now remember when we talked about particles, we said that any amount of mass is equivalent to some amount of energy due to Einstein's, yes, that guy again, because of Einstein's relationship. So recall that delta E is delta M C squared, okay? So delta M times C squared, so the mass deficit times C squared is the energy. So it's some form of energy, right? So what kind of energy is that? Is the energy needed to create the nucleus, okay? It's called, so this delta E, it's called the binding energy. of the nucleus. Therefore, it's also, since it's the energy needed to create this nucleus, it's also the energy needed to rip it apart, to destroy it, okay? So it's also the energy needed to break the nucleus apart. Okay, so B, if that's how you denote the binding energy, so we're not going to be using delta E, we will be using B equals to delta M C squared, where B is the binding energy, okay? And let's go calculate this binding energy, okay? So for lithium-6, which is the example we used earlier, delta E is, we found it to be 5.43 times 10 to the negative 29 kilograms times 3 times 10 to the 8 squared. Always use parentheses, guys, when you take the square of this of the speed of light. So if we carry this calculation on, we will find 89 times 10 to the negative 12 joules. And if we convert to EVs, we will find 30.54 MeVs. And I remind you that 1 electron volt is 1.6 times 10 to the negative 19 joules. Right? So that's the binding energy of lithium-6. And one thing that is going to come in handy is to convert one atomic mass unit, so the mass contained in one atomic mass unit, into MeVs. So let's go see that. So note that one atomic mass unit is 1.66 times 10 to the negative 27 kilograms. So if we convert that to MeVs, we will find that E is 1.66 times 10 to the negative 27 kilograms times 3 times 10 to the 8 squared. So this is 1U, this is C squared. And if we do this calculation, we will find 933.75 MeVs. So one atomic mass unit is equal to 1.66 times 10 to the negative 27 kilograms, and also equal to 933.75 MeVs. Okay, now let's go see another thing that is very important in nuclear physics. It's called the binding energy per nucleus. So, per nucleon, I'm sorry. If we divide the binding energy by the mass number, so binding energy over the mass number, we find what is called the binding energy per nucleon. So this is a number between 2 MeVs per nucleon to about, I think 8.4 MeVs per nucleon. And we will talk more about it, but let's go find that for lithium-6, since we just calculated the binding energy. So for lithium-6, B was 30.46 MeVs. So if I divide to find B to find the binding energy per nucleon, we divide by 6. So B over A is 5.08 MeVs per nucleon for lithium-6. So what does this signify? It's the energy needed to remove one nucleon from lithium-6 on average, okay? So B over A is the energy needed to remove one nucleon, either a proton or a neutron. Okay, let's go do another example of finding the binding energy for a nucleus and then the binding energy per nucleon. Let's do the carbon-12, which is kind of a special case. You will see why. So the mass deficit is 6 times the mass of the proton plus 6 times the mass of the neutron minus the mass of carbon-12. So that's 6 times 1.007276 atomic mass units for protons plus 6 times 1.008665 atomic mass units for neutron minus 12U. Okay, remember that the atomic mass unit is defined as the 1/12 of the mass of carbon-12. So there it is. So for carbon-12, the atomic mass is 12U. Okay. So this is equal to 0.095646U, which corresponds to, I'm gonna convert this immediately to MeVs. So it's 89.1 MeVs. But this is a mass. Mass is not energy, right? So we have to divide with c squared. And to see this, recall that binding energy is delta M times c squared. So delta M is binding energy over c squared. So here is my binding energy. Sorry, here is my binding energy. And here I divide by c squared. So MeV over c squared is a unit of mass, actually. So it's another unit of mass we can use. So now let's go find the binding energy per nucleon. So binding energy per nucleon for carbon-12 is equal to 89.09 MeV over 12, because that's the atomic mass of carbon, and we find 7.42 MeV per nucleon. Okay, so I'm gonna write it here that in general B over A is about 2 to 8 MeVs per nucleon for all nuclei. The higher the B over A, binding energy per nucleon, the more stable the nucleus. This is something you need to know. And again, I'm going to repeat that B over A is the energy to extract one nucleon. We can actually plot the binding energy per nucleon as a function of A for various nuclei, and that reveals many information about nuclei. Okay, I'm gonna try this for the first time. Let's go see this chart. Okay, let's see, paste. Okay, I found this from Wikipedia and I thought it's easier than me trying to sketch things because I'm a terrible sketcher. Can you say that? Anyway, so oops, let me try to fix this. Okay, I hope you can see it, guys. Okay, let me get my pen back. All right, so let's go see some of these traits. I'm gonna provide the link to Wikipedia if you like. Now, let's notice a few things. First of all, they have iron 56 shown with the label there. So we see that the binding energy per nucleus. So by the way, if we go down, this is 56, okay? And the binding energy per nucleon for iron 56 is about 8.5, I think. So this is in MeVs, you can see it here, okay? And if we go very far, actually it's 8.8 now that I see my notes. So that's the highest. So iron 56 has the highest binding energy per nucleon for all nuclei in nature, okay? Now if we go far to the right in the region of very, very super heavy nuclei, like uranium-235 and uranium-238, the binding energy per nucleon is about, what is it, 7.5, so something like 7.5 MeV per nucleon. Okay, so for this nuclei, it makes sense that they split into nuclei with lighter mass. So if uranium-235 splits into a nucleus of mass number 100, for example, and another nucleus with mass number 135, it will create two nuclei with higher binding energy per nucleon. So this is the nucleus with A equal to 100, and this is the nucleus with A equal to 135, say, okay? So if uranium-235 splits, it will create more stable nuclei, because recall that the higher the binding energy per nucleon, the more stable a nucleus is, okay? And this is indeed the case. So nuclei to the right of iron 56 want to split. So nuclear fission, as they call it officially, means the splitting of nuclei. So nuclei heavier than iron 56 split to form more stable nuclei. Okay. Now, if we go to the right of this chart, we see that, okay, I mean, they also include hydrogen that has a binding energy of 0 because it's just one proton. Okay. But the first nucleus that they show here is hydrogen 2, which is known as deuterium. It has a binding energy per nucleon of about 1. So it's the lowest bound nucleus in nature. And then if we go up, you see how helium-3 has a very low binding energy per nucleon. But then helium-4 is very stable. See, it has a binding energy per nucleon of 7 compared to a binding energy per nucleon of 2.5 for helium-3. So helium-4 is a very stable nucleus, okay? The same is true. So here's helium-4. Carbon-12 is also very stable. Oxygen-16 is also very stable. Notice how there are peaks there, local peaks, as we go along the chart. So helium-4 is a peak, carbon-12 is a peak, etc. But lithium-6 has a very low binding energy per nucleon compared to helium-4. Only 5.3, we found it earlier, right? Is it 5.3? I don't remember. Where is it? 5.1, actually. Okay, I'm sorry. But anyway, the point is that nuclei to the left of iron 56, so in this region, let me use green color, okay? Nuclei in this region, they want to perform fusion, okay? Fusion means, so fusion, and the arrow points to the right because lighter nuclei want to fuse into more heavy nuclei. So if we fuse, for example, helium-4 and carbon-12, this guy and this guy, we will get oxygen-16, which is to the right of both of these nuclei and has a higher binding energy than both carbon-12 and helium-4. Okay, whereas if we go to the right in this region of the table, we see that nuclei want to go to the left. Okay, so they want to move towards iron 56, whereas nuclei to the left of iron 56 want to move to the right. Okay, so this is the high mass number region, and this is the low mass region. Okay, I hope this helps, and let's move on. Okay, let's formalize what we just saw with the table. So for low mass number, nuclei have low binding energy per nucleon, okay, except the peaks we saw, except helium-4, carbon-12, oxygen-16, neon-20 is also in there, etc. Notice how all these nuclei are multiples of helium-4. I mean, if we fuse 3 helium-4 atoms, we will get a carbon-12 atom. If we fuse 4 helium-4 atoms, we will get an oxygen-16 atom, etc. Okay, so in the low mass region, the electromagnetic forces, are weak. Therefore, we can fuse elements into elements with high binding energy per nucleon. So what I mean by that is, for example, if we have helium-4, it has 2 protons, right? So you will have 2 positive charges. And if we want to fuse it with, say, carbon-12, we will have 6 positive charges, okay? So this is helium-4, and this is carbon-12. And, okay, you have an electrostatic repulsion, but you can still push through these to form oxygen-16, okay? Whereas this is not possible. I mean, fusion is not possible for heavy nuclei. Like if you have, for example, let's take iron 56 even, it has 26 protons. So fusing an atom with 26 protons with another atom, also with, say, maybe 30 protons, that's a lot of electrostatic repulsion, so it's really hard. You have to provide a lot of energy for that to happen. Whereas for light nuclei, you don't have to provide a lot of energy. And what provides this energy? Stars usually, okay? So inside stars, there's enough energy to fuse elements, okay? Fusion actually happens in stars, as we will see later in this course. Now, in the high mass region, so high A, B over A decreases as A increases, which is what we saw in the table. So nuclei break into nuclei with lower mass number but higher binding energy per nucleon. So this process is called fission. And yes, fission is responsible for the atomic bombs thrown in Hiroshima and Nagasaki, okay? And this is man-made mostly, and fission is also used in nuclear reactors, so it can be used for good to make energy. I'm a big fan of nuclear reactor, guys. I'm sorry, I studied nuclear physics, so I kind of like, I think nuclear energy is green energy and it's good energy, but I hope politicians see this one day. Sorry, this is off topic. Now, let's move on and talk about fission and fusion, okay? Fission and fusion. We already talked about it, but here I want to make it more mathematical, okay? And tell you a few trivia information that I find cool, and it's also something you need to know. So nuclear fusion, let's start with fusion. So nuclear fusion is what creates energy in stars. And it's where it usually takes place. So it usually, let's say, occurs because in stars we have high densities and the particles have high speeds. Okay. And what else? Yes, I wanted to mention here that fusion is something that is studied around the world. France is actually building a facility called ITER to study nuclear fusion and hopefully make it commercial. There is a facility in California that uses laser beams to bring hydrogen atoms together and fuse them, from what I know. And there is also the tokamak, which is a magnetic cylinder that traps plasma and tries to produce fusion and make it commercial, but that's failing because you need a lot of material, you need a lot of atoms and lots of particles to make this happen. And it's really difficult to reproduce the conditions inside stars here on Earth for obvious reasons, okay? Now let's see an example of fusion. So we have helium-3 fusion with itself. I mean, this is what we will study. So you have 3 helium plus 3 helium producing a helium-4 atom plus 2 hydrogens, okay? The way this works, by the way, is if you add up 3 plus 3, the mass number before, so 3 plus 3 is 6, so A is 6 before, and after we have 4 and 2 hydrogens, so 6 6 protons and neutrons after, and then also the atomic numbers must match. So before we have 2 plus 2, 4, and after we have 2 plus 2 times 1, which is also 4. So this reaction works, okay? So it's the same as in chemistry, from what I remember. I haven't done chemistry in thousands of years, guys, but whatever you have before is whatever you have to have after in nuclear reactions. And before I tell you the energy involved in this reaction, let's also mention that, by the way, helium-3 and helium-4 are called isotopes, okay? Isotopes have the same Z, so both have 2 protons pretty much, but different mass number. Okay, so these are isotopes. Now, I'm going to mention this in passing. You don't need to know it, but there's also another thing called isotone. Isotones have the same number of neutrons, but different number of protons. Okay, but you don't need to know that. So this is what you get when you have a nuclear physicist teaching nuclear decay. I'm sorry, guys. So now the mass of helium-3 is 3.016 029 U. The mass of helium-4 is 4.002603 U. The mass of a proton is something we discussed before. I'm not going to write it again to save some time. And I'm going to write here the mass of the electron for the first time. So 0.00054858 U. And I'm going to put a red color here. This is usually ignored because it's so light, okay? But here we said that we have 2 hydrogens produced. So to be precise, we need to include it. I'm going to show you why. Now, remember the mass deficit that we discussed before? We use the same principle here to find the energy produced in fusion. So delta M is the mass of particles before. So mass before minus mass after. So in our case, what's the mass before? We have 2 times mass of helium-3 minus the mass after. We have a helium-4 nucleus plus, minus, because this is still the mass after, right? So minus 2 times the mass of the proton plus 2 times the mass of the electron. Why do I include this mass of the electron? Because that's 2 times the mass of hydrogen 1, okay? If they told us that a proton is produced instead after, then we wouldn't have to include the mass of the electron. But here, because we are dealing with hydrogen, we have to include the mass of the electron, to be precise. If we plug the numbers in, we find that this reaction has a mass deficit of 0.013806 atomic mass units. And if we convert this to energy, can do this alone, I'm going to provide the final result. We get 12.89 MeVs. Okay. So, by the way, I'm going to have a recommendation for you. Maybe I'm going to put it in a link in the description. In the Moon movie, so Moon movie, it was out in 2009, if I remember correctly. They discussed the harvesting of helium-3 from the moon because the moon is rich in helium-3. The reason for that is that there's a lot of radiation from the sun, and helium-3 is absorbed by the rocks in the moon. Okay, so one idea that humanity has is to harvest helium-3 and use it for fusion if we ever find an efficient way to make fusion happen, because it's one of those reactions that is kind of well studied. Okay, so I'm gonna mention a few things before moving on. Okay, so notes. First one, 1 mole of helium-3 weighs 3 grams. How do I know that? Because 1 atomic mass unit is equivalent to 1 gram per mole. Therefore, for helium-3, we have 3 atomic mass units. Okay, precisely 3.00 something atomic mass units. So we have 3 grams per mole. So I'm trying to say this is an infinitesimally small quantity of gas. Okay, so 1 mole of helium-3 weighs 3 grams and has, by definition, 1 mole has 6.022 times 10 to the 23 particles, right? Due to Avogadro's number. Recall that Na, Avogadro's number is 0.022 particles per mole. So 1 mole has 6.022 times 10 to the 23 particles. So 3 grams of helium-3 contain this many particles. So if we fuse this, so fusing 1 mole of helium-3 yields, how much energy will we get? Let's see. So we have 6.022 times 10 to the 23 particles, times for each from each fusion we get 12.89 times 10 to the 6 MEVs and EVs, because I already converted to EVs by multiplying with 10 to the 6. By the way, I'm taking the energy from there. So 12.89 times 10 to the 6 times 1.6 times 10 to the negative 19 EVs, joules per electron volt. We find 1.24 times 10 to the 12 joules. So just to give you an idea of how enormous this amount of energy is, I'm going to give you the fact that a power plant produces about 10 to the 16 joules per year. Okay, so 1 mole of helium-3, if fused, produces enough energy to, I don't know, to light up a city for a day or something like that, which is crazy, right? It's just 3 grams, it's nothing. Okay, and let's go see one more thing that I find important. The mass deficit for helium-3 is 2 times the mass of the proton plus the mass of the neutron minus the mass of helium-3. Okay, so that's equal to 0.00718 U's. So the binding energy, which is delta M times C squared, is 6.721 MeVs. So B over A, the binding energy per nucleon, is, we have to divide by 3. We find 2.24 MeVs per nucleon. Okay, so by fusing helium-3, we get helium-4 that has a higher binding energy per nucleon, as promised, right? Remember when we saw the chart, we said that by fusion we get more stable elements, so here it is. All right, now the next topic, the next thing I want to talk about is actually yeah, let me see. Let's talk about fission. Okay, use a clean page. So fission. Sorry, I was looking into my notes and trying to think about how to proceed. So we talked about fusion and how it produces lots of energy. It also produces more stable nuclei. So let's talk about fission. What kind of uses does it have? So unfortunately, weapons, okay, but also medicine. So nuclear fission is used to produce isotopes that are needed in medicine and also in nuclear reactors. And I already said that I am a big proponent of nuclear reactors. So fission also creates nuclei with higher binding energy per nucleon, with higher B over A than the initial nucleus. And another thing before moving on is that spontaneous fission is possible. So it's something that happens, but it's rare. It's rare. So it's the only known cases are californium-252 and I think uranium-235 and other elements as well, but it's really rare. Like it happens very, very rarely. So 252 californium and then uranium-235, but rare. Okay, so it's not something that happens spontaneously very frequently. And usually, not usually, actually always, to have fission. So for fission, a bullet, as we would call it, is used, which is the neutron. Okay, so the bullet is the neutron. So I'm going to write it in parentheses, a neutron, since it has no charge. Okay, so hitting a neutron directing a neutron towards uranium-235, for example, is like hitting a cue ball in the billiard table to break the balls and stuff like that. So let's see some examples of fission and how much energy is involved in this kind of process. So the first example, and one of the most popular, is that you have your bullet, the neutron, plus 235 uranium. Uranium has 92 protons. This produces, I think it's called lanthanum, 147 and 57 protons, plus bromium with 87 mass number and 35 protons, plus 2 neutrons. Okay. So again, the rule for this reaction to happen is that the mass number before, which is 1 for the neutron, actually forgot to write, maybe I should write 1 for the neutron, and for this neutron here, okay, let me erase. For this neutron, we have 2 and then 1 neutron. Okay, so the mass number before is 1 plus 235, which is 236. And after we have 147 plus 87 plus 2, which also adds to 236. Now for Z, by the way, sorry guys, I got confused. So the neutron has 0 atomic number because it has no charge, remember? So I have to write N10 there. Okay, now Z before is 235 and Z after is 57. What did I say? Sorry. Z before is 92 and Z after is 57 plus 35, which is also 92. So this reaction is possible. Now, how do we find the mass deficit for this reaction? So delta M, again, it's the mass of the parents, pretty much, I mean, these guys, minus the mass of the daughters, you can say. So this might be confusing. So let me erase it. So mass deficit is the mass of the reactants. So mass of the neutron plus mass of uranium-235 minus the products, the mass of the products, which is mass of the lanthanum minus mass of bromium minus 2 times the mass of the neutron. Okay, so for the neutron, we have 1.008655 atomic mass units, plus the atomic mass of uranium-235 is 235.0439 atomic mass units, minus for lanthanum, we have 146.9284 atomic mass units, minus 8692 U minus 2 times 1.008655 U for the 2 neutrons. Notice, by the way, that for most elements, their atomic mass is about equal to the atomic mass number times U, pretty much, okay? But this has to be given to you. Anyway, if we make these calculations, we find 0.186245 atomic mass units for the mass deficit, so delta E. So that mass deficit converts to energy pretty much, so we use delta M C squared. So we get 173.9 MeV, okay? Thus, if we have 1 mole of 235 uranium, which now weighs 235 grams. So it's significantly heavy, but not that heavy, okay? So it's like 235 grams is probably your phone, okay? The weight of your phone or something like that. The mass of your phone, sorry. So if we have 1 mole of uranium-235, we will get, and let's assume that this mole undergoes fission. This mole will produce, and again, 1 mole contains 6 times 10 to the 23rd particles, 6.022 times 10 to the 23 particles times 173.9 MeV, 1 MeV is 10 to the 6 electron volts. 1 electron volt is 1.6 times 10 to the negative 19 joules. So this energy comes to 1.68 times 10 to the 13 joules, which is comparable to what we got before, but 1 order of magnitude higher. So this is the energy produced by the fission of 1 mole of uranium. And this is the principle used in nuclear bombs, pretty much. So, and let's write one rule, because I feel like it was being confusing. So, in nuclear physics, I mean, when we deal with reactions and we want to find the mass deficit, if we have a nucleus X plus a nucleus Y producing a nucleus Z and a nucleus W, these are the reactants and these are the products, then delta M is given by the mass deficit is the mass of the reactants minus the mass of the products. Okay, so this is what you can use to find the mass deficit, and then using that mass deficit, you of course use delta E equals to delta MC squared to find how much energy you can get out of some particular reaction. Okay.